Alright, welcome back. So we're in Module 5, and we're going to talk about supervised learning. Now, it's been brought up a few times already in different discussions or different videos that have been provided. But we're going to dig into it and get a better understanding of what supervised is, and at the same time, kind of get an idea of what unsupervised learning is. So this content is provided by Intel to the college, and it's a great resource for us. I'm just going to follow along with what they've got and add to it as we go. So by the time we get done, we're going to have a great understanding of what the data science workflow is, and it's something we've already talked about to a degree in previous modules. We're going to explain how to formulate a supervised learning problem, and we're going to compare the difference between training and inference. We're going to be able to describe the dangers of overfitting and what overfitting is, and the difference between training and testing data. Well, lastly, we're going to identify advantages of the Pi data ecosystem. Okay, so let's jump on into this, and we'll talk about machine learning. Machine learning is something that we've talked about over and over again in different modules leading up to now. We haven't dug deep into it, and we're going to dig a little bit deeper into it in this module, and in the next module we're actually going to apply machine learning with a hands-on using Orange and do some data mining with not using any programming language. It's code free, but we're going to apply these concepts in the next module. So let's look at what's the difference between supervised learning and unsupervised learning. Well, with supervised, we've got different data points, and we know what the outcome is going to be based on specific data points. If this value, then this outcome. And one of the things that we'll talk about in a little bit when it comes to supervised learning is we use it quite often for classification. And for classification, let's say I wanted to determine if students were short, average, or tall in height. Well, where do those values come from? Well, somebody determines what those values are. We have a known outcome. If you are over a specific value, then you would be classified as tall. If you were between two values, say you're average, and if you were below a specific value, you would be classified as short. Now, those are known, and we set whatever those parameters are. We determine the rules, if you will. And that's what makes it supervised. We tell the system, here are the rules, go work out the rest for us. Unsupervised, we don't know what the important stuff is to be able to determine tall, short, or average. We just don't know. And we tell the system, go classify everybody from this group into 3 groupings, 3 classes, if you will. And that classification thing, we'll talk more and more about it as we go on the future modules. So in unsupervised, we don't tell the system what the rules are. The system goes and figures out what the rules are and then determines the members of each class. As I said, we'll deal with this in the coming modules. We'll actually apply using Orange to do that code-free example in a future module. Now, one of the things that you'll see quite often, not just in this course, but if you're in the AI program, you'll see it in future courses. Is one of the most commonly used data sets is the iris data set. And the iris data set has three different types of iris flowers, or iris, the plant itself. And in that data set, we have different measurements of the flowers themselves: the sepal length, the sepal width, the petal length, the petal width, and then we have known values. So supervised, we have known values. We say, all right, we're going to predict based on these measures whether it's going to be Virginica or Setosa or Versicolor. And with what we're going to talk about here coming up, the system will look at these values and learn based on existing classifications what's important and what's not important. So we call these features, and we see them as columns in data frames in Python. We see them as columns in databases. But in data science, we call these features about the different rows or records. All right. Now, this last column is not a feature. This is our target. This is our classification. The ultimate goal of what we would want to do is to be able to classify the flowers based on the data that we've collected. So if, let's say I have a flower, I don't know which kind of flower it is, and I go measure it. If I've taken this data and trained a model using this data, I can then take just the data with no known species or class, and the system will, to a high degree of reliability, predict what class or which species that flower is. So that's supervised learning. Okay. So we've got to come up with this little roadmap, if you will, of how we determine what a supervised learning problem is. So we'll define the steps or phases of it. So we have an ultimate goal. And in this example, I want to figure out if email is spam or not. So we're going to classify each email as either spam or not spam. And one of the things that we've looked at previously is our collection of data, and we're cleaning data, and we'll talk more about that in the next module. But ultimately, I have these emails, and I want to be able to have a system that will look at every email that comes in and predict whether it's spam or not spam. So here's our outcome. What's our target classification? Our input is known emails that are spam, known emails that are not spam. Now, what do we have along with those emails? Well, we've got the text in the email, maybe the subject line, the time it was spent, the domain it was sent from. There's so many different features that we can collect about the email. And these known values that we feed into this supervised learning program or this model will help us to train this model way of doing things to be efficient and effective in our classification of emails as spam or not spam. Target, classification, that's that last column. In between, all the features. Okay. The data we have are the emails, the historical emails labeled as spam or not spam. So this is known values. That makes this supervised. So we see, living in Florida, we see that if we get on the turnpike or we get on toll roads, that we will be billed for a toll, billed by plate. And essentially what we're talking about here is what's happening as we drive down the interstate, whether it's I-95 or the turnpike. There are cameras that capture an image. So in this example, we're going to predict if this is a stop sign or not. Or, before we do that, we want to predict the location of the bounding box around an object. So there's different problems that we could come up with. The initial problem, we've got a bounding box. Is it around the object or is it over the object in some areas? So that's what's going on here, but this leads to the same kind of concept applied to, is that a stop sign? Yes, it is. The bounding box concept essentially means that we're attempting to isolate an object in an image or a segment of an image. Once we have isolated an object within an image or a selection of an image, we can then apply another model that determines, is this a stop sign or not? Now, when we think about this, we've got a lot going on. A lot of the things that we've said over the past is the ability to use AI. We've been allowed to use AI, or AI has been enabled as a result of our computer hardware, the growth in computer hardware and software. Now, we want to be efficient in everything that we do. And we'll talk more about that in future modules, but I talk about it as often as I can. Be efficient in what we do. So if I want to analyze this image to determine if there's a stop sign there, well, the first thing I need to do is determine, is there an object in the image that could potentially be a stop sign? If there were no objects that could even potentially be a stop sign, why waste time trying to determine if it is a stop sign or not? So we've got different levels that we'll go through, different steps that we'll go through in the AI process. So we've got our data science workflow, and we've got to determine what the problem is. We've got our problem statement. What is it we're trying to do? What data do you need to solve that problem? Do you have it? Is there a cost associated with it? Is it reliable? There's so much goes into this. And the planning part of it is the most significant aspect of it. What happens on the back end is quite easy. What happens on the front end determines how accurate the results will be. So the more work we do up front, the clearer we are on what we do up front, the better the result. So we've identified the data that's important, where it's going to come from, is it reliable? And then we go explore it and do some pre-processing and we clean it. Get rid of stuff that doesn't matter. Could be outliers. Let's say that we're looking at employee incomes and all of a sudden somebody made $100 last year. Well, that's an outlier. That's nowhere near the norm. That will statistically throw off the results. Now, it could be the opposite way as well. You've got a value that's super high. That's an outlier. What if you had a missing value? We've got an individual, we've got a record for them, but we have no salary in there for them. That's a problem. So we've got to go through and clean our data and make sure everything is the way it's supposed to be, so that now when we feed that data into our model, it can actually do what it needs to do. It's got all the tools, all the resources, if you will, to do the work that we want it to do. Now, the modeling part of it, this is huge. And there's a phrase that I use a lot that is, what works for one person may not work for everybody else. What works for everybody else may not work for that one person. Same thing holds true to models. Now, there are a variety of different models available to us. We'll talk about some of them as we go through this course, but it's more for other courses. We don't need to dig that deep, but we'll use some models as examples, especially when we're talking about classification. We'll talk about, in the next couple of modules, we'll talk about k-nearest neighbors. And in the k-nearest neighbors model, if I'm trying to figure out what class an object is in, I look at the objects around it, and if I say k nearest neighbor, k is a variable, I don't know, I can change it. So it'd be the 5 neighbors closest to it, the 10 neighbors closest to it, and depending on that variable, it'll change the results of the model. But in essence, we're judging an object or predicting an object based on the values of the neighbors close to it. Now, I've talked about this before, and in research that I do for skin cancer diagnosis, I do hair inpainting, where we digitally remove a hair from an image, and then we inpaint or replace those pixels that were deleted with predicted values. How do we know what pixel would be there, what the value of the pixel would be, or what color that pixel will be? We look at the neighbors, look at those cells around it, if you will, or the skin around it. So that's a specific type of model. Now, that model may work in some problems and not work in others. So over time, you learn what models work in different scenarios, and we tweak the models as we go along, fine-tune them, if you will, with different hyperparameters. And I test it. I go back and I validate and say, did I solve the problem that I had? The model that I've created, that I've trained, it learned how to predict, classify flowers or whatever it may be. Is it reliable? Or am I overfitting? We'll talk about that a little bit later on. So the validation is, I go check to see, did it work? Is it doing what it's supposed to be doing? And then I communicate with the stakeholders, or I implement whatever this model may be, or the solution may be. So we said spam emails. Let's say that the current model to predict spam, man, it works. High reliability. 6 months from now, it's not working like it used to. That's because the data being fed into it has changed over time, and that model may not apply to the data as it's changed. We may need to retrain that model based on new data. Once I've retrained it, wow, it's more effective again. So there's our data science workflow. Now, what problem are you trying to solve? What data do you need to solve it? How should you clean your data so your model can use it? Build a model to solve your problem. Did you solve it? And then you deploy it. Okay. So as we get into supervised learning, we'll start out with a labeled data set. As I mentioned, the iris data set is something that is quite commonly used, and you'll see it used in a number of the videos that are provided in the resources pages in this course. So we create this labeled data set. It could be an existing data set, or it could be a data set that we create, where we collect the data. Now, where this data comes from, it's a big deal. Is it reliable? Is it consistent? Is it accurate? All these things make a difference. Then we've got to choose the model we're going to use. This is something that the more you've been exposed to something, the more you know about it. There may be a model out there that would work great for what you're doing, but you've never heard of it. So this is one of those, the more you grow, the more you know. So we've got to consistently grow and explore, read, test new models on existing problems and see, hey, does this work better than what I've been using or what previous researchers have done? And then we need to come up with a metric, some way to evaluate the performance of the model. This is a big deal because what we're using are statistics. And I can make statistics say something far different than the actual reality that you see going on. So we need to know what measure we're going to use, and does that accurately evaluate what we're doing. I can have a metric that really has nothing to do with the accuracy of the model, but it really makes that model look good. Look, he's at 99%. Well, the measure, what you're measuring, is not a good accuracy measure. So there's different ways to measure the accuracy of a model. That's something we'll talk more about when we're looking at different models. And we need to choose an optimization method. Now, there's standard methods to use for the different models and metrics when it comes to the optimization. All right. How do you find the model configuration that gives you the best performance? Now, I may come up with a model, and as I noted before, there's hyperparameters that I can change, and the optimization of it is one of those hyperparameters. So there's things I can change, or let's say settings that I can modify. It's not just, here's a standard model, go with it. Here's a model, and there's all kinds of settings that I can go in and modify. And as I used the example before about nearest neighbors, well, how many neighbors? The closest 3, the closest 10. In these models, the training, how many cycles we go through or how many epochs we go through. How long do you spend training this model? That's a hyperparameter, and it's important. So when we try to figure out what model, here's a couple of different models, decision tree, and here's the nearest neighbors that I mentioned. So when we see this example, we can kind of draw lines based on the ones around it. Now, if I had a point that existed right about here, let's say the 5 nearest neighbors would predict what that value would be. Now, it's clearly here across that line, but there are more neighbors, if you will, that are closer to it in the green. And it would predict it as green based on the nearest neighbors. We've got decision trees that help us to make decisions as we go down through. I want to find out what the weather's going to be. Well, let's look at it. We want to predict the weather. Is it sunny or is it cloudy? How dark are the clouds? What's the humidity? What's the temperature? Is it windy? All these things come into play when they want to predict the weather. So that's a decision tree. Each of those is a different model. So when we try to figure out which model we're going to use, there's a lot of stuff that we need to think about. The time needed to do the training, the resources needed to do the training. Now when I say resources, I may have mentioned this in a previous lecture video, but there was an assignment that I had when I was in grad school, and the professor wanted us to perform a prediction based on DNA strings. And I said, here's the model I'm going to use. And it was a model that I was not familiar with. And she said, that'll be interesting. I'd like to see what happens with that. And I should have known with that response what was going to go on. But I quickly found that for me to do that prediction, for that model to work on the resources I had, the hardware I had available to me, I couldn't live long enough for that system to process all of the data to be able to do the predictions, because there was so much work that had to be done. So there's a lot of stuff we need to take into consideration when it comes to a model. Some models take a lot of time. Some models need a lot of processors. Some models require a lot of data. How complex is the problem that we're dealing with? Right. Now, there's a tendency to overcomplicate something that is quite simple. I want to classify this as A or B. It seems pretty easy. A lot of times we overthink it in the processes. Well, I've got all this data. Let me bring all this stuff in. It depends on how we're going about it, the model, on what we would need. Okay. Let's see the type of data we're talking about. Traditional variables that we've been using before, numbers, words. We're talking about images, video. They're all data. Sound. So I'd mentioned the evaluation metric. We need to figure out what is it that makes our model effective or accurate. How well are the predictions matching the true values? I'm going to look at the accuracy. Well, how often did you hit your target? Well, how often did I hit my target? How big was the target? They show an example here, and this is somebody doing archery. What if this target was 100 feet across and you hit it every time? Man, you're a great archer. You hit the target every time. Somebody else had a target that was much smaller. The accuracy, how many times did you hit and how many times did you miss, on a smaller target. So that's the accuracy. The mean squared error, or MSE, is the average squared distance between the prediction and the true value. So here's the formula for it. It's not something we're digging into in this class, but it is something that you would end up having to deal with in one of the other courses on down the road in this degree program that this initial CAI1001 course is in. Okay. So when I said I can make the statistics look really good when in reality they're not good. Well, I want Jim to look like a great archer. Look, he hit the target every time. Yeah, because the bullseye is 3 feet across. So it can be misleading. I want to make sure that how I'm measuring it, the metrics I use, what the settings are, what the hyperparameters are, these things allow me to effectively determine, is it really working or not? So the wrong metric can be misleading, or it may not even capture the real problem. Based on the numbers, it looked great, but no. So I go through and I train the model. Let's say I had a small sample of emails to work with. And of the samples I had to work with, small sample size, maybe 10 emails. That's what I used to train it. And every email that I tested on that model that I built using 10 emails, the initial data, every email was accurate when it came to predicting it. Well, it's misleading because the sample was so small, it wasn't an accurate one. And then when I take an email that's nothing like the ones that I trained the model on, it's going to say, oh, well, this is spam. It may not be spam. I just didn't have enough data to train it effectively. Or I used a metric that was wrong for whatever that model may be. Okay. So I say training. Traditionally, I'll have a data set available to me, and I will break it up into two groupings: a training set and a test set. And the training data is what I use to train the model. The test set is what they're known values. I know if they're spam or not. These are the records that I send into the system, and the system just looks at the features and says, oh, that's spam, that's not spam. And then once it's predicted, it looks at what it predicted and what the actual classification was for that record in the test data. From there, we can determine how correct were you. Now, with that, we know if you were right or not. We want that number to be high, but it may be high because the metric we're using, the way we calculate it, is a little off. Now, optimization configures the model for its best performance. And I'd mentioned before about hyperparameters. And that's the fine-tuning of the model. Let's add more epochs. Instead of 10 epochs, let's go through 100 epochs, and it goes through 100 times instead of 10. And practices over and over again. Think about it like you're going in the gym. Well, clearly, instead of going to the gym 1 day a week, if I went in 4 days a week, I'm going to get better results. Maybe. There's a concept of diminishing returns. At a certain point, you keep going, but it's not going to yield any improvement in the outcome. Knowing that, we would determine at what point are we wasting time or wasting resources, and the going back and forth and testing the models and fine-tuning the models, we see which configuration of optimization is best for us. So with these pieces, a model can now be trained to find the best configuration. We've got different images. We've got forward and backward propagation, not something we're going to deal with in this course. We want to determine what type of image is this. Is it bicycle, human, strawberry? Let's classify it. And it learns on the training set, and then when it's all said and done, we run the test set through it and find out how good's our model, how accurate is it. So inference and predictions, they're not the same. Once a model is trained, we can provide new examples for predictions. I can predict what it's going to be. I don't know if it's a bicycle, but let me run it through. I think it's going to be a bicycle. I think it will. Based on the data I have, I can infer it's highly likely that's going to be a bicycle. Well, we have to classify it. We got to put it in one of those three buckets. Let's throw it in the bicycle bucket. All right, our prediction is bicycle. So we've got inferences and we've got predictions. It's just semantics in a way. When we look at the model, and in this, we're going through and we train the model. The model's learned how to classify it. We send in the test set. That's our inference. And it says, well, all right, let's predict. Is this going to be bicycle? What's it going to be? So in the coding side of it, we'll see three different things that are really important. Train, test, and pred, or the prediction. Okay. And based on that, we come up with some reliability. So the difference between the training and the inference, the training is where this model learns how to do what it's supposed to do. The inference is where we're coming up with a prediction. All right, I don't know what it is. Let's figure it out based on what we learned from the training. All right, that's a bicycle. All right. So the inference is the process. The prediction is the result. So we're talking about supervised learning. Train a model with known values. So we've got data with known values. We've got a model. We fit that together and we come up with a trained model. Now, this is not something I'm going to dig deep into. We'll dig deeper into what the fit part of it is in another course. But once we come up with a trained model, then we run through and we do our inference, where we run data without any classification, feed it into that trained model, and we end up with our prediction. So this is the inference path. Now, there's a concept called overfitting. Training we've talked about, and testing data we've talked about. This overfitting. Now, over time, if we say here's where we're at. Here's our data, our x-axis and our y-axis. We end up with this curve. And the system ultimately tries to fit a curve to the data. And essentially, the model is trying, as it's being trained, it's trying to learn how to be accurate 100% of the time. That's the end goal, is to be 100% accurate. Rarely going to be, you may get 99, high 99 point whatevers, but at a certain point, depending on the hyperparameters and the model that we've used, the way we've optimized it, we may be overfitting or underfitting. Now, overfitting, it's like you're trying too hard. You think you know all the answers, and you're just saying, well, this is there, I got this. Underfitting, now you're just kind of willy-nilly making predictions. Are you really trying? Are you using the data that you need to be using? If you're overfitting, it's like being overly confident. So the curve can be way simple, and we'll call it underfitting. It's a poor fit on the training data, poor fit on the unseen data, and we don't see this getting better as we go along. And as you learn, you would traditionally see your failure go down. So here's our iterations, and we're failing less and less. Here's overfitting. It's all over. We got a good fit on the training. That's where I said, yeah, I got this. I know how to predict. But then when you go and run test data through it, yeah, you didn't know. You didn't have a clue. So that's the difference between overfitting and underfitting. We want to avoid overfitting. We want a well fit. So here's our curve. Everything's right there. Here's our curve on overfitting. You're trying too hard. And here's underfitting. You're not trying hard enough. I say you, it's the model itself. Now, I mentioned this previously. I've got a data set of iris data. I divide it up. I may do an 80-20 set. 80% of them training, and 20% I'll set aside for testing. So the ones that are going to be testing set, they're not used in training at all. Now, what could come up when we do this? How could there be a problem with this? This sounds like a great idea. We'll just segment it out. What if I had outliers in my test set? What if I had a lot of outliers in my training set and no outliers in testing set? Will this impact the results? Absolutely. So here we go through, we train, and then we do our inference, come up with a prediction. Now, one of the things that happens along the way, and I said we'll talk about this more future courses, but what happens here, this back and forth, if you will, the model puts weights. I said there's epochs that we go through, epochs. We go through these things over and over again. The model, as it goes through trying to learn from the training in certain models and certain types of systems, it'll go through and it'll put weights. We may determine what the weights are. The system may determine what the weights are. If I put weights on the different features, it will learn based on those weights. What if I didn't set the weights? Well, that's unsupervised. I don't set the weights. What's important, that's unsupervised. When we talk about model weights, we're looking at the difference between supervised and unsupervised. Okay. I'm not going to dig deep into Python. I'm not even really going to dig into Python in this. Okay. Python's the most commonly used language. This isn't a programming class. This is a general overview of AI. We're not coding, but we will use Orange in a future module, a couple of future modules. Okay. So this part of it we're not going to dig into. Okay, so with this said, I've got a variety of different resources available to you. I'm not going to overwhelm you with resources in this module. Go do research, go through and look at the different things that we've covered already, the different videos that may have talked about supervised, unsupervised. What we're talking about now is machine learning. We've alluded to deep learning, and we'll talk more about deep learning. I think we're dealing with deep learning in Module 7. Okay, so we still got a couple to go. Make sure you got a good grasp on what machine learning is, how it differs from just normal data science, data analytics, and the difference between supervised and unsupervised. We're focusing on supervised right now. Okay. As we get into deep learning and move on, we'll dig a little deeper into the unsupervised, but that's, like I said, most of it's beyond the scope of what we're going to deal with here. Okay. All right, I'm going to jump into something real quick before we let out here. I'm going to jump over to another tab, and here's the quiz that's in Module 5. Now this quiz is associated with LinkedIn Learning. Now, there's a number of videos here available to you. And if we click on this, it's going to say, hey, do you want to start a free month? No. You want to buy for my team? No. Don't need to. All I want you to do is go through 48 seconds, 45 seconds, a minute, another minute here, 3-4 minutes here, 6 minutes here. Go through these videos. I'll pop through one by one, explaining what machine learning is and how it applies to what we're doing. Okay. So, once you've gone through these, you don't have access to the quizzes, but the same kind of content that you would have in these quizzes is what you will see in this quiz. Okay, so go through those videos, get a good understanding of what's taking place in those videos. It's about 2 hours of videos. A minute, 2, 3, 4, 5, 6 minutes at a shot. Once you've gone through it, then come over here, take this. There's no login. You don't have to create an account or start a free trial. Okay. Now once you've gone through the videos, take the quiz. You can take it as many times as you want until it closes. Okay. So be aware of the due dates and what you need to do to get through this. Okay. Aside from that, you've got Module 5 discussion, help each other out there, and discuss some topics. And as always, take part in that reflection that you got to get completed. Let us know, how did you do? What worked? What didn't work? Things do you like or maybe not like about this module or the course as a whole? Okay. Now, with that said, see you in another video or another module.